So our next speaker, I'm pleased to announce, is Zhenong Jin, who is a professor at the University of Minnesota. He was actually trained as an agroecologist, and his research integrates process-based models, remote sensing, and machine learning approaches. And I also will mention that he was a lead crop scientist at Atlas AI, so he also has industrial experience. With that, I will turn it over to Zhenong Jin. Thank you.
Okay, thank you. We're really glad to present here to share our experience when investigating the kgml approach for agriculture. And today I will give 2 examples for modeling N2O emission, is a nitrous oxide, a kind of greenhouse gas, and ecohydrology. And I would particularly thank our contributing author, without who this talk is not likely to happen. So why agriculture? Because agriculture is at the hotspot for fighting climate change. So agriculture contributes to about 1/4 of the global greenhouse gas emission, and with 15% comes directly from agriculture production, and about 10% through the land use change. Mainly happening in the tropical region where people converted tropical forests into the cropland. And in the US, okay, so agriculture contributes to about 10% of total emission. And if we further break it down, the 10%, we see nearly half of them come from the soil fertilization, maybe when we apply nitrogen NPK fertilizer. Okay, and the majority of the emission is in form of N2O, nitrous oxide gas. And N2O is about 265 times more powerful than carbon dioxide as a greenhouse gas. Now, the problem with the N2O emission, the farmers usually over-apply fertilizer, because with the changing weather condition and the interaction with soil, it's just so hard to predict what's the optimal nitrogen they should apply every year, every season. So as a way to do the insurance, they usually apply more fertilizer than necessary, because fertilizer is cheap, but yield losses caused by under-fertilization is a problem. And this usually leads to over application of the nitrogen fertilizer. And then this is a serious problem to the air pollution, to water pollution, and also land degradation. And recently we saw a surge of interest in sustainability, and many of the larger corporations, they have committed to achieve net zero emission by 2030. For example, here, Cargill, all the food industry company have agenda to cut their greenhouse gas emission, and Microsoft, Amazon, they want to reach net carbon neutral operation by mid of the century. Now, carbon offset from agriculture is one of the popular solutions to mitigate the carbon emission. And according to the report by Soil Health Institute, if farmers can change their current practice, there's a huge potential to cut the greenhouse gas emission. For example, if they optimize the grazing management, they optimize the nitrogen management, if they adopt a cover crop to sequestrate this carbon dioxide from the atmosphere, or if they adopt a no-till, change from the conventional tillage practice as a way to prevent the soil carbon to break it down and then gradually release back into the atmosphere. So here's both a surging demand for carbon offsets, and agriculture can provide a potential supply. But there's also a question or concerns by different group of scientists who suggest to say, okay, even if you do this kind of practice, because there are not, many of them are not permanent and vulnerable to goes back into the atmosphere. So the actual carbon sequestration potential by agriculture may be small, or much smaller than what the advocates are suggesting. But for sure, all those practices, they belong to the conservation practices or regenerative practices, which benefit to soil health and more broadly to our environment. But regardless of the debates, the agricultural carbon market is already around the corner. It's happening in Europe, it's happening in China, it's happening in the US. So here is a brief illustration of how agricultural carbon market works. It starts with data collection through soil sampling. We set up a benchmark like how much the greenhouse gas emission is for a particular field. And then the farmer will adopt the changes. And currently the suggested practice is adopt cover cropping, change from tillage to no-till, reduce nitrogen fertilizer, and diversify the crop rotation. And next, a third-party verifier will come in to verify the carbon removal, but it is a challenge task, which we will discuss in more details later. And then the carbon trading company comes in to buy the carbon credit from farmers and then sold them to the buyers, mostly corporations who want to mitigate or cut their greenhouse gas emission. And once the carbon credit was sold, the money goes back to the farmer for to reward their practice change. Now, a concern here is action does not equal to outcome. And what that means is, for example, two farmers in the southern US versus a farmer in Minnesota, if they all add cover crop, the farmer in southern US would expect to increase or sequester 1 ton carbon dioxide per hectare per year, but in Minnesota, it's likely to be only 0.2. So the same action will lead to very different outcome. And even within the Minnesota, the two nearby fields would have a very different outcome. This makes the verified carbon credit a particularly important a step to make the market transparent and rigorous. So here comes the Congress. They have just passed the bipartisan bill called Growing Climate Actions, Growing Climate Solution Act, which asks the USDA to create a certification program and help the landowner, farmers, ranchers, and foresters to navigate through the growing agriculture carbon trading program. And accurate and cost-effective methods for quantifying carbon credits is a fundamental to the agriculture carbon market, because we want to make sure like all the claimed carbon sequestration is real, and we pay every individual farmer fairly and accurately. So this is the quantification is critical to make sure the program does not become an unverified subsidy. And here I use N2 as an example to illustrate what options we have currently for the greenhouse gas emission. And as you can see from the lower parts, emission factor, it's easy to use. You just multiply by a coefficient that turns the nitrogen fertilizer into N2 emission. But the uncertainty is huge. Airborne sensing, mostly by sometimes by hyperspectral sensing, it has a huge potential, and people are excited about this. But overall, the technology is at early stage. And process-based modeling, which simulates the complex feedback between soil, water, atmosphere, crop, is a widely used tool to estimate the greenhouse gas emission. But because of the uncertainty in model inputs, model structure, and model parameter, we expect to see a large errors in any of the estimates. Okay, so what about the kgml for modeling N2O? And to start with, let's ask a question like why estimating N2O is so hard. Now, N2O, briefly, it's coming from two processes, mainly denitrification, but sometimes it could also come from reaction called the nitrification. And N2O emission is hard to estimate or model because it has a hot spot and hot moment pattern across the landscape. And this is because N2O is controlled by a range of biotic and abiotic factors. At the very bottom, that's the weather management and the initial soil status. And then in between, there are many intermediate variables like soil water temperature, soil texture, and how the microbes come in to interact with all the abiotic factor. And this interaction determines the oxygen nitrogen availability, which ultimately drives the N2O fluxes. And so because of the hotspot hot moment pattern of the N2O, we explored lots of different structures for the kgml model. And one promising case we found is from our past work by Dr. Vipin Kumar's group that use kgml to simulate the stream flow. It's similar to N2O because you also expect to see a hotspot hot moment pattern. So the benchmark here is a black box deep neural network model, LSTM, and the experiment here is trying to reproduce a 1,000-year simulation from a SWOT model. Okay, now the domain knowledge can provide guidance on the machine learning model through multiple aspects. The first is simultaneously simulate the interrelated variable. And the second is to distinguish a state versus flux variable. And third is to describe the dependency structure between different intermediate variable and the target variable. And finally is use a physical constraint among the different model. And as you can see from the performance, the physics and the knowledge guidance does improve model performance. So this gives us hope to develop a kgml model for N2O emission. So experiment overview, we use the synthetic data and observation data to explore feature importance and their causal relationship as a foundation to design our kgml model structure. Now we use synthetic data to pre-train the kgml, mainly to initialize the initial condition and the weights. And the real observation data was used to retrain the model and refine the kgml. And the left out observation data will be used to evaluate the kgml. We generate our synthetic data from an advanced ecosystem, agroecosystem model called ecosys. So ecosys, like many of the crop models, explicitly simulates water, energy, carbon, and nitrogen cycle. But importantly, ecosys is mostly built on physical and biochemical rules, and not so much based on empirical relationships, so that you have to tune a lot of parameters. And in that way, we believe ecosystem is the ideal model to provide the domain knowledge. And we have validated ecosystem using 7 FluxNet sites for agriculture across the US. And here's the experiment we used to generate the synthetic data. Now the real observational data. First, I have to mention the high quality N2O measurement is very limited. And and more often they only observe N2O fluxes along with a limited biotic and abiotic variables. And here, this data set from mesocosm experiment is unique because it measures N2O, but also many intermediate variables like the carbon dioxide fluxes, soil moisture, and some soil chemical indicators, so that we can use them to diagnose our kgml model, the intermediate stage. And so we tried a different structure, and it turns out the GRU outperformed the LSTM as a benchmark pure machine learning model. And the kgm model is developed also based on GRU, but has more knowledge guidance. And the lower part, the GRU cells are used to represent the driving variable and also intermediate states of the system. And the upper part mimics the biogeochemistry reaction that for nitrification and denitrification. So let's take a look at the results. Okay, so kgml model, it does outperform the pure machine learning model, the GRU. And I want you to particularly pay attention to some of the peaks, which is the key aspects we want to capture, the peak fluxes. And as you can see, the red kgml prediction can more or less capture the real observation, but the GRU in blue doesn't do a good job in many of the cases. Now, the other interesting part is out of the growing season, the GRU model without domain knowledge guidance predict a high emission peak in the winter time. But based on our domain knowledge, we know it's not likely to happen in the controlled greenhouse. So, but in contrast, the kgml model, it's pre-trained with the ecosystem model. So it has a domain knowledge inside, does not make a fake prediction. So this also suggests the kgml model with the pre-training to assimilate domain knowledge does do a good job compared to pure machine learning model. Now, you may wonder, how about the original agroecosystem model? Here's the result. Same chamber year simulated by ecosystem. And you can compare the two. R-squared IMSE, it's worse than the pure machine learning model and also the kgml model. So we also compare to many other tree-based model and the simple neural network model. And kgml model is always significantly better than other benchmarks. So our next step is to expand the kgml model with more gold standard data coming from FluxNet. And also recently, the ARPA-E has founded a smart farm program to collect the gold standard data with hot moment and hot spots incorporated in the experiment design. So we discussed the kgml model for a mesocosm experiment, but our ultimate goal is to monitor and model greenhouse gas emission for every field across the US. So here we introduce a framework that says agricultural outcome, crop yield, greenhouse gas emission is the interaction between crop, traits, management condition, and environmental condition. Now, oftentimes, let's use a modeling a net ecosystem exchange, the CO2 flux between land and the atmosphere as an example. So oftentimes when people do the modeling, they only have environmental information, weather, soil. As you can see, the performance is really bad. And if we can collect information on management, for example, when you plan to harvest the crop and a bunch of others, you can improve the model performance. And if you have information about crop traits, like the variety, the maturity group, and their responses to different environmental stresses, we could significantly improve the accuracy of model prediction. So the key here is we need to derive the hyperlocal observation, and we need a way to scaling the field collection, no longer based on sampling, but more on low-cost sensor and hyperspectral imaging as labeled. And we need a high-performance computing switch from process-based model to kgml surrogate model. And this is a system solution we're proposing, because we believe now at the current stage, none of the single methods can solve the problem. So we need a harmonized collaboration between the different methods. So here I give you an example what I meant by the scalable satellite information. And and similarly for IoT sensors. So here is an example of 10-meter daily ET product for the US coming from Caillou Guan's lab at the UIUC. And as you can see here, the best ET performed much better compared to the state-of-art LXET. And the nice thing about this is for any of the field, we could have a real-time or near real-time observation as long as the satellite data become available. So here, blue line is the estimation from best ET, and black is the observation. In most cases, it tracks the real observation coming from eddy covariance tower. And this is a state-of-the-art satellite product. Now, let's zoom out to revisit the big picture. Our food system currently emits about 12 gigatons CO2 per year. And if we do nothing, it will increase to 15 gigatons by 2050, even if we can keep the yield increase. So we don't clearing too much tropical land. But actually, we need to achieve a 4 gigaton per year emission target if we want to limit our global warming under 2 Celsius degree, or even 0 gigaton for 1.5 degree. So what we can do. And according to the World Resources Institute, coordinated action is needed. And it includes like reduce food waste and change the diet, and increase the food production, which mainly would come from breeding program, and increase fishery supply and reduce emission from the production. Mostly, it's would achieved by nitrogen and manure fertilizer management, and also protect and restore natural ecosystem. So many of the solution has some connection to the talks in the subsequent, the following sessions. So yeah, really coordinated efforts is needed to limit the global climate change. And with that, I would thank you for your attention. And if you're interested in machine learning model and kgml model for agriculture, we are hiring PhD students and postdocs, and welcome to contact.
Thank you so much, Zhenong. There are no questions on Slido yet, but I had a question, if you don't mind. Mm-hmm. So you mentioned the Growing Climate Solutions Act, right? That was just enacted in June. I was just curious, how has that changed your work? I mean, there must have been a huge influx of interest ever since that came through, right?
Yeah, definitely. So first, we expect there's a huge resources coming in to invest in this domain, and what I and my collaborators, we really believe the science community should figure out a technical roadmap where the resources should be invested strategically, because we are talking about a big number coming from the federal government. And I think now, as an example, for AI research, there's ImageNet. But for agriculture, there's not. We are always dealing with messy, sometimes trash data. So the fundamental thing we first need to do is maybe create ImageNet for agriculture. And those should be achieved by expanding more of the golden standard data collection.
Great. And I'm pretty sure we will hear a lot more about your research based on the demand, the big demand. And now the questions come in like crazy. So here's the first question. How can you expand the kgml application you developed?
Sorry, could you expand the question?
It's a slightly vague question, but gives you more chance to broaden. How can you expand the kgml application you developed?
Okay, so I guess there's a, let's look at the structure. First, there's lots of things to do and upgrading the structure. And we are collaborating closely with the computer science group here. And the other promising stuff, I think, is being able to assimilate real-time observational data. And there's about more than 2,000 or close to 3,000 satellites going around the Earth. So it provides a huge number of data to provide the constraint to the kgml model. And so developing a flexible structure that is able to assimilate the satellite IoT sensor data to make real-time prediction. I think it would be very promising direction down the road.
All right, next popular question. Could you use the combination of model output and observations to guide deployment of observation platforms, i.e. what quantities would be most useful to observe?
Yes, that's a very good question, and that's actually what we want to do. So partly, like earlier in this slides, we use the causal relationship analysis to identify, okay, here's a few key variables to measure. And with some initial measurements, we could have a sense of where is the hotspots and the hot moment in the across the landscape. So from both aspects, the modeling approach can provide initial knowledge to guide where we should deploy more sensor and what variable we should pay attention to.
Thank you.